Hello and welcome to this little module where we're going to continue our study of self-adjoint operators. Okay, so the previous two properties we saw already hopefully were interesting to you. Whatever the matrix may be, as long as it's self-adjoint, the eigenvalues have to be real. As long as it's self-adjoint, the eigenvectors corresponding to distinct eigenvalues have to be orthogonal. Okay, so that's very powerful properties. Later on, like I said, we'll see maybe in the next week, we'll see some applications of self-adjoint operators and you'll see how these properties are crucial. Okay. Now, even more interesting is the fact that self-adjoint operators are always diagonalizable. Okay. Now, we saw earlier that diagonalizable operators are particularly easy to work with because in one particular basis the operator becomes diagonal, which means diagonal matrices are very nice, right? They just scale the coordinates. So, in some basis it is diagonalizable, that itself is nice, but what is more interesting about self-adjoint operators are orthogonally diagonalizable. Okay, so not just diagonalizable, they are orthogonally diagonalizable. Okay, watch out for this orthogonal now. So, there is an orthonormal basis with respect to which a self-adjoint operator becomes diagonal. Okay, so that's a very powerful property and we'll see that now. Okay, so hopefully you see why this is non-trivial, right? So if you have eigenvalues with higher multiplicities, it's not clear that eigenvectors have to exist of the same dimension, right? The geometric multiplicity may not be equal to algebraic multiplicity, and it was not easy to nail that down, isn't it? Geometric multiplicity and algebraic multiplicity are complicated things to nail down. Okay, so if you're self-adjoint, it means it's diagonalizable, which means all algebraic multiplicities are equal to geometric multiplicity. So these are all very non-trivial facts to ensure for a matrix, and just being self-adjoint, just making sure A equals A Hermitian ensures all of these properties for the eigenvalues and eigenvectors. So let's see a proof for this. It's actually quite an easy proof. You'll be surprised at how easy and elegant this proof is. We will use this very simple result and you'll see everything will fall. Okay. So, but one important constraint here is I will restrain myself to Cn to Cn. I'll go to complex numbers because that's where this is easy. Of course, complex is okay because real also is contained in it. So, I'm going to start with an operator t from Cn to Cn and t is equal to t star. Okay, so it's self-adjoint complex. Okay, and only in those cases it's easier to write down like this. At least the proof I'm going to present works in that case. Okay, so we'll start with Shor's theorem. Shor's theorem, we know what it is, right? So we know that any operator is upper triangular with respect to some basis. Now, in fact, any operator in an inner product space is upper triangular with respect to an orthonormal basis u1 to u1. Okay, so this is Shor's theorem. We saw how to do it, right? You take the upper triangular basis and then simply do the orthonormalization, Gram-Schmidt orthonormalization. Gram-Schmidt orthonormalization preserves the upper triangularity of the matrix, so that carries on. Okay, so any operator T has an upper triangular matrix representation with respect to an orthonormal basis u1 to u1. Okay, here is the clincher. This is the crux of the argument and it's really nice. It turns out if the operator is self-adjoint, okay, so for any operator you have upper triangular with respect to orthonormal basis. On top of it, if the operator is self-adjoint, t equals t star is satisfied, then in fact t ends up being diagonal with respect to the same Shor basis. Okay, so if you have a self-adjoint operator, whatever basis with which you are normally getting upper triangular, you will magically get diagonal itself because of the self-orthogonal, self-adjoint property. Self-adjoint property is very sharp. It's very easy to prove this. There is nothing in this proof, right? Why? Because you look at the matrix of T within the Shor basis. It could be upper triangular, right? So the diagonal element can be something, and then the lower triangular has to be 0. Upper triangular could be something. In general, this could be the case. But then I want T to be equal to T star, which means A has to be equal to A Hermitian. How will A be equal to A Hermitian? Only if this guy is 0, right? This guy has to be 0 and the diagonal elements have to be real. Okay, that's it. It's as simple as that. There's nothing in that. So if you look at this matrix, an upper triangular matrix, if it has to be self-adjoint, it better be diagonal with real elements on the diagonal. What else can it be, right? So you can't get anything else. So just by the Shor's theorem, you automatically get in the Shor basis that a matrix of a self-adjoint T has to be diagonal itself. Okay, so that means self-adjoint operators are diagonalizable, of course, with respect to an orthonormal basis. The Shor basis is orthonormal. So self-adjoint operators are truly special because of this property. There is an orthonormal basis, right, like a canonical basis, but orthonormal basis is almost like canonical, right? So everything that you have with canonical, you also have with an orthonormal basis. So, with respect to an orthonormal basis, some orthonormal basis, the self-adjoint operator is just diagonal. It is just scaling the coordinates. It makes it so simple to deal with self-adjoint operators. Okay, so this part is extremely critical. So let's dwell on these properties a little bit more. So I'll define these definitions and properties more clearly. First of all, these self-adjoint operators have symmetry in the matrix structure. We saw that already. A matrix A satisfying A equals A Hermitian is called Hermitian symmetric or Hermitian. Self-adjoint operators are also called Hermitian operators. This is a common term in physics, particularly people call it Hermitian. So that comes because of this Hermitian symmetry. A equals A Hermitian, right? Now, if A is real, then this A Hermitian is the same as A transpose, and if you have A equals A transpose, such a matrix is called symmetric. Okay, not just Hermitian symmetric, just symmetric, because there's no conjugate there. So this is a definition. So a lot of people will call self-adjoint operators as symmetric operators and all that, Hermitian operators, and these matrices are called symmetric matrices. So this is one terminology that you should be comfortable with. Now, I made this remark about multiplicity earlier. Basically, just by ensuring A equals A transpose in a real case, or A equals A Hermitian, geometric multiplicity has to be equal to algebraic multiplicity, because the the upper triangular matrix becomes diagonal, then all your multiplicity arguments work perfectly. Okay, so it's diagonalizable. Now, finally, the orthonormal diagonalizability for self-adjoint operators is truly special. Okay, so the reason is the Shor's theorem basis, right? The orthonormal basis of eigenvectors for a self-adjoint operator simply makes the matrix diagonal because of the A equals A Hermitian requirement. With respect to an orthonormal basis, it has to be self-adjoint, so A has to be equal to A Hermitian. So you cannot have upper triangular with non-zero up on the upper triangular part, right? Everything has to be 0. Okay, so crucially, self-adjoint operators are simply scaling of coordinates with respect to some orthonormal basis. Okay, so in some sense, self-adjoint operators are like diagonal matrices, right? They are not different from diagonal matrices, so they're easy to deal with. As operators, they're very easy to understand, but they're also rich. They do a lot of things. They can do a lot of things in practice. So you can model a lot of things with self-adjoint operators. You can't model everything with just straightforward diagonal operators and canonical basis, right? You will need some self-adjoint operators to come up with models for very often. But luckily, self-adjoint operators, because of the symmetry, because of the way eigenvalues, eigenvectors work, they are orthonormally diagonalizable. They are as good as diagonal. You can work with them pretty much like diagonal case. Okay, so that's a very nice property that you have. Okay, so let's close with a few examples of problems. So here is a problem, a bunch of self-adjoint operators, and you have to diagonalize them. Okay, so in these kind of problems, I think the tricky aspect is to find the eigenvalues and eigenvectors. Okay, so in some cases, maybe you can sort of see where the eigenvalues, eigenvectors will come from. In some cases, you may not be able to see. For instance, some of the tricks are you should first check if 1 1 1 will be an eigenvalue, eigenvector, right? So for instance, 5 plus 1 plus minus 3, it's just 3 3 3. The row sums are constant, so 1 1 1 will be an eigenvector and the eigenvalue will be 6, right? So once you find one eigenvalue 6, right? 1 1 1 eigenvector, eigenvalue 6. Okay, so you may be able to guess other things also. Sometimes, in some cases you may be able to guess it, but you may not be able to also. But once you have one eigenvalue, it's easy to find the other two eigenvalues in a 3 by 3 case, right? So you can write out the full equation if you like. One factor, so you can factor it out, you'll get a quadratic, you can solve it. So that's one way of doing it, or you can smartly try and figure out if anything else is true. But so finding the eigenvalue, eigenvector is slightly non-trivial. So later on we'll see some numerical methods. There'll be one part of it, substantial lecture, I'll devote to just feeding it into a computer program and it will tell you the eigenvalues, eigenvectors. So it's not very hard in practice, but if you want to theoretically do some calculations, you may have to be innovative about coming up with eigenvectors, eigenvalues. So here, like I said, one eigenvalue is 6. If you have to find the other eigenvalue, maybe one can quickly do this. So I have, I'm just trying to see if there is any other obvious eigenvalue. I don't know if you can see that. So 1 1 1 is an eigenvector with eigenvalue 6, right? So that is very clear here. Just that comes from the, oh, I'm sorry, eigenvalue 3. So, sorry about that. I think 3, right? 1, 1, 1 is an eigenvector with eigenvalue 3. So that seems very clear. The trace is also very useful. Trace is, it's got like trace of 19. So the other two eigenvalues have to add up to 8, and the eigenvalues are going to be real, right? So these eigenvalues are real. So all these things are additional hints. So let me see if there is, it doesn't seem to be very obvious that you will get 8 somewhere. So you can do the phi minus lambda determinant equal to 0 thing here, right? So that's one way of doing it. That's right. So you equate this to 0. So this determinant you'll have to write down. It's a bit of a pain. So right. So minus 1 into 9 minus lambda. This also is minus 9, right? Minus 3 into minus 3 plus 3 into 5 minus lambda. So this is the equation that you get here, and let's just write it down. So you have 5 minus lambda whole squared times 9 minus lambda. Maybe we'll get lucky and we'll get a nice simplification. I don't know, right? Can't be so sure. This is 9 minus lambda minus 9, so 9 and 9 is going to cancel, and you'll get just a plus lambda. Okay, this guy is not going to be so nice. So anyway, there is a plus 9, right? And then there is a minus 9 into 5 minus lambda. Okay. Okay, so this is where we are. We can try and simplify this. I'm not sure if, yeah, I think it works. So notice if you see how the factorization may work out. 9 minus lambda. You may want to simplify this. So you get here. Yeah, so we'll just do it in a dumb way. I think you can do it a bit smartly if you like. Plus 9 minus 45 plus 9 lambda, right? So you get here what? Equal to 0. So I'm just writing it down. I hope this works out. So you have your minus 90, so minus 81. Okay, so this is what we get here, plus 19 lambda. 0. So this seems like a little unfortunate, but that's okay. So you have to factor out a lambda minus 3. So I was hoping you'll get something like that there, but it doesn't seem to work out quite easily. So you'll have to do this in the hard way, minus 10 lambda plus lambda square. So hopefully I have not made any mistakes. So this is probably the most painful way to do this problem, but anyway, I mean, this is one question you can do like that. So 25 into 9, that is 225. It's becoming really ugly. So 25 minus 90 is minus 115 lambda, right? Yeah. And then you have 9 plus 10 squared plus 19 lambda squared, okay, minus lambda cubed minus 81 plus 19 lambda equals 0. So finally you're going to get lambda cubed minus 19 lambda squared, and then 115 minus 19 is going to be 96, isn't it? So you have plus 96 lambda, and then 225 minus 81, that is 144 minus 144 equals 0. So it looks a little nasty. I hope that's okay, but 19 has to come because that's the trace, so that's okay. So so from here you can do a lot of things. You can do quite a few things which are interesting. I know one root is 3, so you can try to find the other root very cleverly. So if you want, you can you know the 3 will factor. Okay, so you're going to write lambda squared, and then what should happen here? So it should be minus 16 lambda, isn't it? Only then you will get 19 lambda squared. So you get 3 lambda squared minus 16 lambda, so minus 19 lambda squared, and then the other factor has to work out. So you know the constant is 144, you have minus 3 here, so it's going to be, that's just divided by 3, which is just 48. Okay, so you can check that 96 also works out. If you look at plus 48, that's 96. So this factors correctly. So 3 is one eigenvalue. We always saw that. If you have to do this, this is going to be 12 and 4, right? 12 and 4 will work out. So you have lambda minus 3 times lambda minus 4 times lambda minus 12 equals 0. So that is this guy. So the eigenvalues are 3, 4 and 12. Okay, slightly more painful way to do it. So eigenvalues are 4 and then eigenvalue is 12, and then you have to try and find, if you have to do 4, then it will be, so this is I am going to do mentally, right. So for 4, the matrix for which I have to find null space is 1, 1, minus 3, minus 3, minus 3, and then 4 is just 5 here, right. So this one, you have to find null space, you say that these two are equal, right. So 1 minus 1, 0 will be a eigenvector with eigenvalue 4. Okay, I hope you see this. So this is the way in which you can quickly see that this is working out. So you can see the orthogonality, right? So 1, 1, 1 and 1 minus 1, 0 are orthogonal. These 2, 3 and 4 are distinct eigenvalues. So now you may also look at 12. So if you have to do 12, then you have to subtract 12 here. So you'll get minus 7, 1, minus 3, 1, minus 7, minus 3, minus 3, minus 3, and then 9 minus 12 is minus 3. Okay. All right. So now you have to find the null space here. Seems a little tricky. Yeah. So finding the null space here seems a little bit tricky. So is there a quick way to do it? So I might have to do the elimination myself, right? So let's do this elimination. So I'll do this minus this. So I'll do this minus this. So I'm getting 0 here, minus 8 here, minus 8, plus 8 here, right? This minus this. Then again, this minus this will go 0, minus 4, 4. Okay. So this is just 2 minus R1. Then this minus 2. Minus 2 here, if I do, then I'll get minus 3, 0, 0, 1, minus 8, this minus half, right, this minus half, so 0, and then minus 7, 8, 0. So this is what you get here. So you see that it's working out. So you'll have to pick the first guy as free, you can pick it as 1, and then if you do that, the second guy will also become 1. So you have 1, 1. Okay, so if you do 1, 1, then it has to become minus 2. So it looks like 1, 1, minus 2 is an eigenvector with eigenvalue 12. Okay, so let's check that. 1, 1, minus 2. Yeah, so 1, 1 is 6, and then minus 2 is plus 12 here. 1, 1, minus 2 is working out, and all these guys are all orthogonal to each other. Okay, so I hope you see this. It's a very nice, simple illustration of how to do eigenvalue, eigenvector calculation by hand, but nobody does it these days. You just put it into a computer program, you'll get the answer, but I'm just showing you one case by which you can do this. So this is how you do that, and you can check all the orthogonality, it works out. Look at the second problem. The second problem looks really complicated. It says 6, 0, minus 2, 0, 0, 6, 0, minus 2, and all of these things. It looks quite a bit complicated, but you can try and guess some things. Like for instance, you can guess that 1, 1, 1, 1 is an eigenvector, okay, and then you can also see that 1, 1, minus 1 will be an eigenvector. You can keep guessing like that with just 1, 1, minus 1, minus 1. The structure also tells you something like this is true. There's also a circulant structure here, right? You see the circulant structure, 6, 0, minus 2, 0, 0 goes on top, 6 comes below. So you can also guess based on the Fourier basis. You will get a Fourier basis here given the circulant structure. So you can guess the eigenvectors either using the structure of the matrix or some idea. So you get 1, 1, 1, 1, and you can use the Fourier basis. This is just n equals 4. So you can use the Fourier basis if you want. You can also use other things. There are other ways to guess the eigenvector here. So you can use these ideas. So I'm not going into detail here. So it's just one example, or just throw it into a computer program. You'll get some answer and you can look at it. This has got very simple eigenvalues and eigenvectors. Okay. So the third question is also this is also self-adjoint, right? So second is also self-adjoint, by the way. Third is also self-adjoint. It's got minus I here, as you can see the conjugate transpose is the same as itself. So all the eigenvalues are real, and it's also got a circulant structure. Do you see the circulant structure here? So 2i minus I, so it will go up here minus I, 2i minus I 2. So the eigenvectors will come from the Fourier basis. So once you put the Fourier basis eigenvectors, even here the eigenvectors will come from Fourier basis. Once you put the Fourier basis, you can quickly compute the eigenvalues. Okay, so maybe the third one alone I'll show you. The second one I'll leave as an exercise. You can do the Fourier basis or some other basis. Third one I'll show you how it's easy because of the self-adjoint plus the circulant makes your job really easy in guessing eigenvalues. So here is the matrix. It goes 2 minus I, if I'm not wrong, minus I 2. Did I get it right? Minus I, right? I2 minus I, sorry. And then minus I2. Okay. So you can see this is self-adjoint, right? So you can see this is self-adjoint. It's also circulant. Okay. So once you know it's circulant, one of the eigenvectors, the eigenvector, so one of the eigenvectors is 1, 1, 1. The other two eigenvectors, or you can put this w equals e power I 2 pi by 3, which is minus half plus root 3 by 2 I, right? And then omega squared, which is e power I 4 pi by 3, which is minus half minus root 3 by 2 I. We've seen all this. So these guys are they end up being eigenvectors. So this is an eigenvector. Okay, we know the eigenvalue has to be real. So all these things are going to work out. So if you multiply by 1, 1, 1, you will get this minus I plus I will go off to 0. So you will get 2, 2, 2, isn't it? With the eigenvalue 2. Okay, so it's quite easy to check this. And the next one is 1 omega omega squared, isn't it? So if you do 1 omega omega squared, and if you're going to multiply on the right, you're going to get minus half. So it's enough if you multiply the first guy, and we know it's an eigenvector, so all of those things will work out. So if you multiply the first guy, it's got 1 also, so it's easy to see. So you're going to multiply 2 times 1 plus minus I times omega, which is minus half plus root 3 by 2 I, plus I times omega squared, which is minus half minus root 3 by 2 I, and this is going to be equal to, notice how these cancellations will happen. This part will cancel when you multiply the half and the minus half, and the other part will give you minus I squared and a minus I squared here. So both of them will become root 3, so you get 2 plus root 3. Okay. So this is an eigenvector with eigenvalue 2 plus root 3. Okay. So the next one is 1 omega squared, omega power 4, but omega power 4 is the same as omega, right? So because omega power 3 is 1, so omega power 4 is same as omega. So this is an eigenvector with eigenvalue. You can do the same calculation. It's 2 into 1 plus minus I into omega squared. So minus half minus root 3 by 2 I, and then plus I into minus half plus root 3 by 2 I. And you can guess where this will go. This will be 2 minus root 3. Okay, so notice how all the eigenvalues are ending up being real, which is what should happen in a self-adjoint, and the trace is 6. You add the 3, you get 6, and these guys we know are orthonormal, right? So 1, 1, 1. Okay, so these are eigenvectors. So orthogonal in this case, you have to divide by root 3 or root 3 to make it orthonormal if you want it. So that's okay. Okay, so this is a way in which you can quickly find out, and you can see with respect to the Fourier basis, this guy becomes orthonormal. This matrix becomes diagonal, right? It's a nice thing to see. Do something similar for the second problem. In fact, there are easier ways in which you can do it, and you don't need to go to Fourier basis also, but Fourier basis is an easy method. Take a look at that. Okay, so that I'll leave as an exercise to you. Okay, so here is the next question. So you have u1 and u2 being eigenvectors of a self-adjoint operator. Okay, so the first thing you should check is whether u1 and u2 are orthogonal or not, right? So you can check that. If you can check, you see that 1, 1, 1 and 1, 1 minus 2 are indeed orthogonal to each other, right? So the question asks you to find another eigenvector which is not in the span of u1, u2. Okay, first of all, how do you approach this problem? See, first of all, you know that self-adjoint operators have an orthonormal basis of eigenvectors, right? So if I give you these two as eigenvectors, right, and the dimension is only 3, isn't it? So then the third eigenvector has to be orthogonal to both these guys, okay, isn't it? So I mean, you can think of various ways in which that has to happen, but anyway, but you need there is an orthonormal basis of eigenvectors. The first eigenvector seems to be along 1 1 1, second eigenvector is along an orthogonal direction 1 1 minus 2, right? So dot product of these two is 0. Okay, so the third eigenvector better be in the third orthonormal direction. So how do you find the third orthonormal direction? You simply do the Gram-Schmidt orthonormal extension. Okay, what is the Gram-Schmidt orthonormal extension? So you take 1 1 1, you take 1 1 1, u1 to be this. If you want, you can normalize it, it's okay. So 1 1 minus 2, okay. So you can normalize it if you want. U1 cap will be 1 by root 3 times 1 1 1. So u2 hat is 1 1 minus 2, we have to normalize it, it becomes 1 by root 6, which is a important thing to write down. 1 plus 4 is 1 by root 6. To do this, find the third eigenvector. So we know that u1 is one eigenvector, u2 is another eigenvector. We can find the unit vectors in that direction. Now the third eigenvector is going to be orthogonal to both of these guys. So the three eigenvectors have to be orthonormal. So one way of doing this is to do Gram-Schmidt. So how do you do Gram-Schmidt? You have to find another vector here which is not in the span of these two. So be careful about that, finding the vector that is not in the span of these two. For instance, I think 1 0 0 is not in the span of these two. So you can quickly check it. Mistakenly, if you do 0 0 1, then you won't get it, because this 1 0 0 1 is in the span of these two. So you do u1 minus u2, you get 0 0 something. So you have to do something like 1 0 1. Or you can also intelligently guess the third orthonormal direction. Like for instance, it looks like 1 minus 1 0 is the third orthonormal direction, right? So this is what you should get. But if you want to get it formally, you can find this and then do the Gram-Schmidt. If you do a Gram-Schmidt, you will get the answer. You can find a W, which is V minus V inner product u1 hat minus V inner product u2 hat. So, and if you evaluate this, you should get something like this. But 1 minus 1 0 is actually orthogonal to both these guys, right? So that needs to be the third direction, but you can find it sort of in some, let's see, hopefully this will give us the same answer. If you do V comma u1, you get a 1 by root 3, the inner product is 1 by root 3, multiply by 1 by root 3, you get 1 by 3, 1 1 1. And then V comma u2 is 1 by root 6, inner product with that u2 hat is 1 by root 6, then multiplying by u2 hat will give you 1 by 6, 1 comma 1 comma minus 2. Hopefully this will work out correctly, right? So the first value is this is 1 minus 1 by 3 minus 1 by 6, 1 by 3 plus 1 by 6 is 1 by 2, so you have 1 by 2 here, and then the next one is minus 1 by 2, and the last one is 0. So it's working out correctly. So this is W, and that's the same as 1 minus 1 0, and that's what you get as the third eigenvector. So using the orthonormality property, one can find the third eigenvector. So here is another problem which sort of uses all this orthonormality. So you have u1 here, u2 here, and u3 here. These are given as eigenvectors of a self-adjoint operator. Okay, and if the eigenvalue corresponding to u1 is 3, what is the eigenvalue corresponding to u2 and u3? Okay, so now if you notice, u1 and u2 are not orthogonal, right? u1 and u2 are not orthogonal. So if u1 has an eigenvalue 3, u2 better have the same eigenvalue 3. Okay, because if they are unequal, then these two have to be orthogonal. If these are given as eigenvectors already to you, and they are not orthogonal, then they should have the same eigenvalue. Okay, so the eigenvalue of u1 and u2 also has to be 3. So likewise, if you also see u1 and u3 are not orthogonal. Okay, so the eigenvalue corresponding to u1 has to be equal to the eigenvalue corresponding to u3. Okay, so all these three guys have eigenvalue 3. Okay, and if you want to find an orthonormal set of eigenvectors, these two already you can see are orthogonal, right? u2 and u3 are orthogonal. I hope, yeah, that's correct. But u1 is not orthogonal, so you start with u2, u3 and find a third orthogonal direction in the linear combination of these three, right? So you start with u1 1 1 1, do the Gram-Schmidt carefully, you will get the third vector, which is the orthonormal set of eigenvectors. So you find 3 orthonormal set of eigenvectors for the eigenvalue 3. Okay, so these are nice ways to use the properties of eigenvectors and orthonormality and orthogonality to deduce something about the eigenvalues without knowing even what the matrix is or something. Just know partially what it is. You can do some calculations with that also. Okay. So I hope this this gives you a comfort with self-adjoint operators, what they are, how to work with them, how they are plentiful and all that. So in the next week or so, we'll start looking at applications of self-adjoint operators and how they play a crucial role in so many areas of engineering and physics. Okay. Thank you very much.